Is this screen visible? Hello? Can you
Yeah,
guys
we
see
can.
my screen?
Yeah, we can see it.
Okay. So let us wait for few. We can start from, let's say, 6 or 7. Okay, so I think now we can start the session. So welcome you all to this week 6 live session. So in this particular live session, we'll basically solve the quiz of week 5. And at the same time, we'll see the implementation of SVM in Google Colab. So there are certain data sets that we have already dealt with, like MNIST dataset, Cyber10 dataset. So I will be using some sort of synthetic dataset as well as some standard dataset, and we'll be leveraging those two datasets to classify them, and we'll try to classify them, and uh, we'll be using several different versions of SVM like linear SVM, polynomial SVM, etc. etc. So along with that, in the last week, while solving the quiz, I told you that answers that is basically provided by NPTEL. Some of them were wrong. So I mailed them. So they have confirmed that that is under re-evaluation, and some of the answers are indeed they have provided wrong solutions. So therefore, all of you will get marks accordingly, and that will be updated by probably next week. So week 4 marks, again, it is basically re-evaluated and you will get the revised marks by the next week. So that is the announcement that I had to make. Okay. This is the first problem states that which of the following statement is true about logistic regression. So in this particular week, the main content was basically logistic regression, decision tree, and the Markov models. So in case of logistic regression is basically uh, extension of linear regression. In linear regression, the main motive is basically, this is just to illustrate about what is the difference between linear regression and logistic regression. And this particular discussion is basically necessary, and it is basically somewhat linked with the next question as well. So I think discussing it over here would be more appropriate. So for example, in case of linear regression. So in case of linear regression, so there the main aim is basically to fit a curve. It could be it's specifically it's a linear regression. So we basically try to fit a card through different sort of segmental lines. And the equation is also pretty simple. So that is y hat is equals to W transpose X plus T. So where W is basically the weights and B is basically the bias. And these two parameters are basically learnable. So these are called learnable parameters. And you have this is basically the prediction. And you have corresponding. So your data set looks like this over here. Data set is basically paired value. So xi, comma yi. And this is basically the true output, which should be the output. But your linear regression will give you the prediction y hat. So your main aim over there is basically to minimize the loss function. So the loss function is basically you can calculate between yi and yi hat. So in general, we use MSE as the loss function, that is mean square error. That is yi and yi hat. So in general, I can write 1 upon n, where n basically means the total number of elements that you have in the test set or in the prediction set. But we put 1 by 2 due to some reasons. Basically, in the next step, when you do the gradient descent, you have a squared term as well. So for example, if I just write it over here, it is basically I equals to 1 to n. And then over here, it is basically yi minus yi hat a whole square. So now you can see where this is the loss function. So this loss function in the next step, how you can basically optimize the weights. You can optimize the weights by taking the del L by del W. And whenever you take del L by del W, you can see there is a squared term. And in the next term, in the next step, if you take the derivative of this particular thing, the 2 will come over here. So this 1 upon 2 and the multiplication 2, they will cancel each other. They will cancel each other. This is what the basic linear regression basically means. Now, the logistic regression is basically extension of this linear regression. In case of logistic regression, you basically try to predict. Your data set looks like this. You have xi, which is the feature. So this is called feature, and you have yi. So this is now basically represent as label, whereas the yi previously it was true output, which was also a real number. So in case of linear regression, as you are basically trying to generate some new data, or you are trying to fit a card, that means you have to predict some values over there in case of linear regression. Okay, so in case of linear regression, the main funda is basically you're trying to predict some data out of it, which is a real value. So your input x is real number, and output y or y hat, so to say, this is also real number. These are real numbers. But in case of logistic regression, this is basically used for the purpose of classification. And in the class lecture as well, you have seen that Professor M.K. Bhuyan has used an example of type 2 diabetes. Given some feature like weight or something, he has tried to predict whether a person is having type 2 diabetes or not. So now you can understand the logistic regression is basically used for the purpose of classification task, not for the purpose of regression task, which is basically generation of real numbers. So logistic regression is used for classification, whereas linear regression is used to fit a card. That means the main target is basically output should be a real number. Now, what about this particular output? What is this yi? This is a label. So that means this contains only discrete class labels. That means whether it is class number 1, whether it is class number 2. For example, if a person, like in the week's lecture, you have seen that Professor MKB has used the example of whether a person is having type 2 diabetes or not. So let's say if a person is not having any diabetes, that would be class 1. If he or she is having diabetes, that is class 2. So now you can understand you have discrete levels. 1, 2, class 1, class 2, class 3, like that. So that is why I have written over here, this yi is basically, so this is the set of discrete numbers. So given this, these discrete numbers, you can also write them in terms of, this is one aspect is basically this type is discrete. Otherwise, in majority of the cases, while you basically do the coding, there you will see there is a term that is called categorical variable. So categorical variables means what? Categorical variable means these are sort of a string data. String, string data. Now I hope that you all know string. So from the basic notion of C language, you know that what is basically meant by a string. So the example could be, if I just take example could be, you can write non-diabetes and you can write diabetes. So now instead of replacing the classes by class number 1, class number 2 like that, you can just put a string over there. For example, a person is having no diabetes, so the class is non-diabetes, otherwise the class is diabetes. So over here you can see the categorical variable basically means the string type of data. And you are basically trying to predict this categorical variable using the input feature xi. So that means yi basically, you can also write this as discrete or categorical dependent variable. Okay. And the basic equation for logistic regression is basically provided as y hat is basically 1 divided by 1 plus e to the power minus w transpose into x plus b. So this particular function is basically a representation of sigmoid function, and y hat basically you map the uh, uh, you map the input to the output in the range of 0 to 1. And I have not kept the uh, closed bracket. I have put parenthesis over here. Uh, can anyone just tell me that why, what is the reason that I have not put this particular sign? I could have written 0, 1 within closed bracket, but I have not written that. Why? Anyone? So the reason is if I just plot sigmoid function, so you will see the curve basically looks like this. At 0, the value is 0.5. The moment you increase the value of this particular term, e to the power minus that value, if you increase this particular term over here, the value will tend to reach 1. But when it will reach 1, that is basically if you put the value as infinity, then 1 divided by 1 plus e to the power minus infinity, then you can just formulate by yourself, you'll see that you will get 1. So that means when this particular term will tend to infinity, then only this particular graph will touch the value that is 1. Similarly, the value will reach 0 at minus infinity. So these sort of curves, these are called asymptotic curve. This sort of asymptotic curve also you have seen, for example, ideal gas characteristics, PV characteristics, where basically the parabola basically reaches to 0 when x tends to infinity, like that. So that is why I have written that the values basically touches either 0 or 1 based on whether they reach to either minus infinity or plus infinity, which is basically non-realizable. So that is why I have I have kept them within parenthesis, not within the closed bracket. So this is a mathematical notation. But the main point is basically the range of the data output from the logistic regression is in between 0 and 1. So just by this particular discussion, you can see that the logistic regression can be used for classification, and specifically you can use logistic regression for binary classification. So this is the major use of logistic regression in general sense, that logistic regression is basically used for binary classification. At the same time, let's say if you have very less amount of data as well, and the data are linearly separable, let's say you have two classes, and the classes have very distinct properties, then just by putting the logistic regression idea, you can classify these two classes. You just put a decision rule that your yi, which is basically 1 divided by e to the power minus w transpose xi plus b, if this whole thing is greater than equal to 0.5, then the decision will be in the form of omega 1. Let's say this is omega 1. And if the value is less than 0.5, then you can think that the data basically belongs to omega 2. And this is very easy to classify. So that means even with smaller amount of data as well, if the data is quite linearly separable, then you can classify the two sort of data points very easily. So the another major point that I'm discussing is basically this is used for binary classification. Even with smaller amount of data, even with smaller amount of data, you can train logistic regression. Data output range in between 0 and 1 in the from the last slide, what we have seen. And the data output is in the form of discrete categorical dependent variable. Okay. Now let us see what are the statements that is basically provided over here. That let us start with this. Which of the following statement is true about logistic regression? So it states that it is not suitable for binary classification, which is false. Because already we have seen that this is particularly used for binary classification. So this is false. Then let's say it takes a large amount of training data to perform well, which is not, again, it is not true. So it is false because already we have seen that if the data is by and large linearly separable, then it is very easy to classify using logistic regression. You just have to put the value in the sigmoid function, then you have a decision rule. So this is basically the decision rule that you evaluate yi based on the equation of sigmoid function. And then if the value is basically reaches greater than equals to 0.5, then you can take in the decision for class omega 1, else it would be in the form of class omega. So you do not need larger amount of data to train a logistic regression. So the next statement that is basically provided is it is robust to extreme outliers. So this is also false because this logistic regression is not robust on extreme outliers. So if I just again give you a basic example. So for example, let's say this is, let's say you have cat and dog. So this particular example in the last week also I have given. Let's say you have cats and dogs, and in the data set, the dog class comprises, uh, let me just show you some figures. Okay. So let's say you have, in the data set, you have normal cats or normal Indian street dogs in the data set. So you have extracted a feature that is called weight. Weight from both the groups, cats as well as dogs. Now, by the basic notion, we know that in general, the weight of dog is basically much heavier than uh, the, sorry, this is, let's say, sample, and this is the weight. So let's say sample number 1, 2, 3, 4, 5, 6, 7. Let's say the from the cat class, let's say 1, 2, 3, 4, you have calculated the weight. The weight is ranging in this particular, let's say, this particular level. Whereas the dog, from the dog class, if you have calculated the weights, they are ranging in this particular region. So just by changing this particular decision rule, if you want to change this particular decision rule based on this particular scenario, so then let's say uh, your decision rule may be, let's say, if the value is greater than 0.7, then you can consider the case is basically dog class, otherwise it is, let's say, cat class. Now, as I was showing that this is a dog. This is called Chihuahua breed dog. And as you can see from the figure that the shape is quite alike with the cat. So as the weight range as well. So if you calculate weight from this particular dog, so even though it belongs to a dog class, the, the sample will basically lie in the same region as the cat class. So the point is, in the initial data set, you had these green points and red points. Now let's say I have given you some other data. I have given you another dog. You have extracted the value of weight for that particular dog, and you have mapped into this particular two-dimensional plot. So you will see, as because the weight is in general quite less than normal street dogs, and as because it has some similarity with the cats, the weight profile will be same as the weight profile of a cat. So this basically referred as an outlier. Why it is called outlier? That means even though the class identity is dog, but the feature that you have extracted, it basically has the same profile as the other classes weight profile. So this is an example of an outlier. Now, as you can see from the figure itself, your decision rule is if the sigmoid function output is greater than 0.7, then only you can take decision for class dog. Otherwise, you take decision for class cat. So as you can see, the sigmoid output is basically less than 0.7. So obviously, your model will predict that the outlier, even though it is being a dog class, it will label it as, or it will predict it as cat class. So now you can see from this particular figure itself, as you have this sort of an extreme outlier, this is an extreme outlier. your model is not able to perform well. Hence, your model is not robust with respect to the presence of outlier in the data set. So that is why this particular option, the first option, this is incorrect. So as this particular option and so as this one. Now, by sort of elimination rule, you can see that option C is left, which has to be the correct option. But let us try to analyze this particular option as well. So you can see it does not make any assumption about the data distribution, which is true. You can see you have read naive-based classification rule. You have seen the linear discriminant function over there. On the very beginning of the discussion, you you always talked about X, the input feature belongs to normal distribution with mean 0 and some some sigma square. And if your data is basically, so this is the case of univariate feature. And if your data, let's say, is d-dimensional feature, then you talked about a multivariate Gaussian distribution. So therefore, in those topics, so this basically valid for linear discriminant functions and let's say naive Bayes. So over there, you considered that your data is basically coming from normal distribution or Gaussian distribution. However, while choosing, uh, while discussing the logistic regression, we have not considered that your data is basically normally distributed or any sort of a particular distribution, let's say uniform distribution, exponential distribution. We have not talked about this. Our main concern is basically we will be collecting some feature from the data and then we'll try to classify using logistic regression, irrespective of what sort of uh, uh, um, probability density function it belongs to. So that means we do not conceive any pre-notion, do not conceive any pre-notion about specific probability distribution function. So that means we do not talk about any sort of specific probability distribution. It can be any sort of distribution from a data can be sampled, and then we can take some features out of it, and then we can classify using logistic regression. So therefore, this particular option is the correct option. It does not make any sort of prior assumption about the data distribution. Okay, fine. So the next question. So now we'll be able to easily answer these questions because already we have spent a numerous amount of time on this particular discussion, and several points are basically linked with the subsequent questions. So logistic regression is a machine learning algorithm used to predict probability of a dash. So as you can see that the logistic regression output value is basically limited in the range of 0 to 1. So obviously you are getting some sort of notion of probability there in case of logistic regression. Now they're asking that you are basically predicting probability of what? So probability, so the output variable is yi. You are basically getting some sort of probabilistic notion for yi. Now they're asking what is the basically type of yi. So already we have discussed the data output for logistic regression is a discrete or categorical dependent variable. Why dependent variable? Because you are depending on xi, and depending on xi you are basically getting a value of yi. So therefore this is a dependent variable. And specifically what sort of variable this one is, because we are dealing with a classification problem in logistic regression, the output would be either discrete form or it is basically a categorical data. So therefore, output is discrete or categorical dependent variable. So let us see. So over here, you can see that we have categorical dependent variable. So therefore, this is the answer for this particular question. So the next question states that what is the hypothesis of logistic regression? To limit the cost function between 0 and 1, minus 1 and 1, minus infinity, infinity, and 0 to infinity. So already we have seen that if this is the logistic regression function and the argument of the function is x, and this is y basically 1 divided by 1 plus e to the power minus x. So you can see that you are basically putting y of x. So the argument of the function is basically x. So the representation of the data is basically at 0, the value is 0.5. And when you increase the value, it reaches to 1 at infinity. And if you decrease the value, it reaches to 0 at minus infinity. So the value is bounded between 0 to 1. So yi basically bounded between 0 to 1. So therefore, option A is the correct answer. That your cost function is basically bounded between 0 to 1. Okay. The next question basically states that the data set of pass and fail for 5 students are basically given in the table, and they have represented that for 29 hours of study, the result is fail, 15 hours of study, result is fail, and so as for the next uh, observations. Now, calculate the probability of pass for student who studies for 34 hours. Now we have to calculate the probability of pass, for hours equals to 34. So this is what we have been asked over here. And they have given, assume the model suggested by the optimizer for odds of passing. The course is given as they have given some sort of a closed form equation. So can any one of you tell me what is an odd of an event? Let's say you have event A. So what is the odd of that event? Did any one of you solve this particular question? Okay. So let's say, let me just define some basic nomenclatures. Let's say you have an event that is A, and probability of that event is basically, let's say you have n number of trials and occurrence of event A is basically, let's say, Na times. So the probability of A is basically Na divided by N. So this is all of us, we all basically know this particular notion of probability. Probability of A is basically out of all the trials, how many times the trial A basically occurs. Now there is another notion that is called odd of an event. Let's say odd of A is basically defined as probability of event A divided by probability of non-occurrence of event A. So I can write it as odd of A is basically probability of event A is basically P of A. So I can write P of A divided by probability of non-occurrence of A. So if the probability of occurrence is P of A, so the non-occurrence would be 1 minus P of A. Once. So this is what is basically meant by odd of an event. Now let us move to the problem. So in the problem they have given a closed form equation. So probability of odd of pass. So because now the event is basically to uh, pass the exam. So therefore log of odd of pass is equals to minus 64 plus 2 into hours. So now the hour that they have asked us is basically for 34 hours we have to see the probability. So therefore I can write it as minus 64 plus 2 into 34 divided by minus 64 plus 68, that is 4. So log of odd of pass is equals to 4. So I can write odd of pass is basically e to the power 4. So let's say this is relation 1. Now in the question they have asked us to find what is the probability of pass. So we have this particular relation, that is, let's say relation A. So from this particular relation, we can get a closed form solution for P of A. So this is very easy. So I can write it as odd of, from this particular relation, I'm just referring odd of pass multiplied with 1 minus probability of pass is equals to probability of pass. So therefore, probability of pass equals probability of pass 1 plus odd is equals to odd. So inside odd there is this particular argument is there, pass. I am not writing them. So I can write probability of pass is equals to odd of pass divided by 1 plus odd of pass. So already we have uh, retrieved the value of odd of pass. So you can just put it over here, e to the power 4, 1 plus e to the power 4. And shockingly, you can see that this is a representation of logistic regression. So that is basically the function of sigmoid function. So 1 divided by 1 plus e to the power minus 4. So if you evaluate that particular value, you will see the answer, correct answer is 0.982. So that is probability of pass is basically 0.9820. So the next question states that which of the following is used to measure the quality of a split in decision tree. So we already know that decision tree starts from the root tree. Then you have the intermediate nodes, and then at the end you have basically the leaf nodes where we do the classification or let's say regression. So this is the level one. So this is the root nodes. So these are the intermediate nodes, intermediate nodes, and these are basically the nodes. These are basically called the leaf nodes where we do the classification. Let us consider the problem at hand is classification problem. So okay. So now there are certain conditions when you do these sort of splitting. So let's say your data set, in your data set, let's say there is a very popular data set is available that you can see, that is called housing price data set. So the target is basically you have to predict the price of a house, and the uh, independent variables to predict the price of a house are, let's say, what is the location of the house, how many bedrooms are there, how many kitchens are there, likewise. So these are sort of the independent variables, and based on these independent variables like location, how many bedrooms you have. So based on this, you have to predict the price of the house. So this particular data set is basically available in Google Colab as well. If you open the root directory of Google Colab, there you'll see the uh, 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 housing price data set. It is there. It is a by default data in Google Colab. So let's say um, you have to predict the price of the house based on these entities. Now you will start from one sort of entity, let's say location. Then you have certain conditions. If location is, let's say, there are some sort of altitude and longitudes have been given. So latitude and longitudes have been given. So therefore, based on these latitudes and longitudes, will be basically splitting into two different sets. Let's say, either it belongs to uh, A and B latitude longitude, then your decision will go to this particular branch. Otherwise, it will go to this particular branch. Now, how do you make certain decisions that based on these sort of values, you will do the branching of the classification process or the regression process? That is the main thing. So for that, you have certain measures, and these are all also called the quality measures. By observing them, or so to say, by maximizing them, you do the branching of decision tree, and which basically leads to, starting from the root node, which basically leads to the leaf node where we do the classification. And there are certain indices or quality measures by which we can do this. So those measures are, you have seen in the week's lecture, that is called entropy. Then you have Gini index, as well as the very wide, the The popular metric is basically the information gain. So if your information is gain is high for a particular instance or a particular variable, so then based on that, you do the branching of the nodes. So by that logic, information gain is another quite popular uh, uh, quality measure by which you can do the branching of the decision. So over here, they have mentioned all three to do the quality measure of a decision tree while do the branching or splitting of the tree. So therefore, all of the above will be the correct answer. Okay. So the next question basically is a numerical problem on decision tree. So over here, there are 6 instances for attributes A1 and A2. So you have A1 and A2. The input features or attributes with positive or negative classification results. So the classification result is basically they have given plus or minus. These are two classes that you have, either positive class or negative class. So actually the representation should be the classification as because this is a dependent variable. It should come over here rather than putting over putting this particular output in the middle side. It should be in the right hand side. Now, the question states that what is the information gain of A1 relative to these training instances? So that means we have to focus on A1 and we have to see what is the information gain that we can observe from from the point of view of A1 as an input attribute or an input feature. So information gain is basically illustrated as the entropy of the whole set. So over here, the whole set is basically for the all instances that we have. So entropy of the whole set minus summation of the individual subcategory present in each attribute. So that is, I can write as, let's say, Si, and I can take cardinality divided by cardinality of the whole set. So over here we have the whole set multiplied with entropy of Si. So now let us evaluate all these quantities. Let me start with uh, entropy of Si. So what is basically meant by entropy of Si? So we are focusing on uh, input attribute A1, and A1 basically contains two two set of subcategorical variables. So they are either true or false. So we now have to see for each of these conditions that what is the classification result. So these are basically this true and false are basically the S1 and S2. So we have to calculate entropy of S1, which is basically meant by entropy of true, and entropy of S2, which is basically entropy of false, under the consideration that input attribute is A1. So therefore, entropy of true for A1 as an input attribute, I can write it as minus. So the entropy is minus P of X into log 2 P of X and summation of all those components. So I can write it as, so in case of true, these are the true cases. So their total number of samples for two true cases are 1, 2, 3. 3 cases are there. Out of 3, you have positive cases, 2 positive case, 1 negative case. So therefore, let us start from the positive samples. So the probability for positive samples is 2 by 3 into log 2 of 2 by 3 minus. Now let us consider about the negative class data. So minus 1 divided by 3 log 2 1 upon 3. Similarly, entropy for false, given the input attribute is A1, I can represent it as, so for negative class, for the false class, you can see there are uh, uh, 3 sort of instances available. Out of 3 instances, 2 instances are basically belonging to negative classification and 1 is basically for the positive classification. So again, let us start for the positive classification part. So I can write minus 1 upon 3, that is the probability for the positive class. Total number of instances is 3. Positive class ke liye there is only one variable, so therefore 1 upon 3. And then I can write log 2 of 1 upon 3. And again, now we'll be talking about the negative classification results. So there are 2 samples out of 3. So therefore 2 by 3 log 2 by 3. So effectively, if you solve the values, already I have solved this. So let me just write the values directly, 9183. And effectively, if you just look at these two, they are same representation. So therefore 0.9183. At the same time, uh, now we have to find the entropy of the total set, that is S. Now, what is the total set? The total set is basically the classification. So how many instances if you have over here? Total number of instances is 6. Out of 6, 3 are for positive classification, 3 are for negative classification. So entropy of whole set I can write as minus 3 by 6. Why 3 by 6? Let us now talk about the positive classification data. So there are 3 instances for positive class, 1, 2, 3, and total number of instances is how much? 6. So therefore the probability is 3 upon 6 multiplied with log 2 3 upon 6 minus. Now let us talk about the negative classification part. In the negative classification part, you have 3 instances, 1, 2, 3, and the total number of samples that you have, that is 6. So therefore, again, it would be minus 3 upon 6. The probability is 3 upon 6 and log 2 3 upon 6. So if you solve this particular thing, you will get the output as 1. So now we have found out the 2 major components, E of S and E of Si. Now let us try to write the information gain. So information gain Ig is basically entropy of whole set minus cardinality of S true. Cardinality of S true divided by cardinality of S whole multiplied with entropy T, given the input attribute is A1, plus cardinality of false divided by cardinality of whole multiplied with entropy entropy false, given the input attribute is A1. Now let us assimilate the values. So entropy of whole set we have already evaluated, that is 1, minus, so cardinality of true. So cardinality means in a set, how many samples are there that belongs to true uh, true instances. So over here you can see in the whole set, you have total 6 instances. There are total 6 instances. Out of these 6 instances, 3 are for true, 3 are for false. So therefore, it is 3 divided by 6, and the entropy of T1 we have already evaluated 0.9183. Similarly, for cardinality of false, you can see the cardinality of false is 3, and the cardinality of the whole set, that means total number of samples in the whole set is basically 6. Sorry, 6 multiplied with entropy of F. So entropy of F also we have evaluated 0.9183. So if you solve this, you will get the value as 0.0817, which is this. Okay. So this is simple. You know the equation of information gain. You have to evaluate the entropy for each of the cases, and then you just have to plug in the values over here, and then you'll get the final answer. So this is the final answer. Okay. So the next question states that how is pruning used to prevent overfitting of a decision tree?
Sir, excuse me, sir.
Yes, yes, please.
Sir, I have one doubt, sir. Uh,
Yes.
the answer is 0.816. What does it convey, sir? You told the information gain should be high. What does it infer?
Okay. So I think I can take the, because this particular example is not a, a complete example. This is just to infer that we are just intending to calculate the value of information gain over here. But what it basically intends to mean, I think I have to go to the week's lecture and I can download the, from there I can show you what it basically means. Oh, sorry. This is, I think, in week, uh, the next lecture. Just a moment. Okay. So let's say, yeah. So let's say you have a data set like this. So the data set basically, uh, it has certain input attributes. So these are the input attributes. Like what would be the outlook what would be the temperature, humidity, or wind. Based on these four variables, you have to decide whether you will go for tennis or not. So that means, let's say, uh, the problem statement is, if it is very hot, outside is very hot, then you will not play tennis. So therefore, based on these variables, you have to decide whether you'll be playing tennis or not. And how you can do this? Now over here, we are basically learning decision tree, and we'll try to make a decision tree based on the uh, these four categorical variables. Now, how to do that? So let's say you can start like this. I will give you some possibilities. Let's say you can start with Outlook. If let's say Outlook is uh, sunny, there are three conditions that you can see. So sunny, overcast, and rain. So there are three unique uh, categorical representations. So sunny, then overcast, and rain. Now, if you choose Outlook to be now the first question is, how can you choose the root directory, that is the root leaf, that is the root node, sorry. This is the root node. Root node could be Outlook only. You can also take like based on wind characteristics, I will start the decision. You can also start from humidity. Let me think that I will choose humidity, and based on humidity, I will start with the root node, and then I can go to the leaf node. So you can also choose humidity to be the root node. Now the question is, how can we understand be the at each of the nodes? That means at each of the nodes, what should be the attribute? Let's say if I choose wind to be the attribute for classification, from which we can start the classification, it may so happen that you are not able to classify well. Maybe let's say out of uh, 14 data, you are able to classify only 5 data correctly. Majority of the data are misclassified. In the same way, if you choose humidity to be the first node, and based on humidity, you will do the classification ruling, then also you may incur that your uh, classification result is not that good. So you have to choose that which of the categorical variable I should choose at each of these nodes. So I can choose this one, I can choose this one, I can choose this one, and I can choose this one as well. Now the question is, which is the optimal one to choose, and how we can choose this based on the quality measure, and that is the information gain. And the very naive rule is basically, for whichever variable your information gain is high, that you will put in the node. And how to do that? So over here they have calculated. So in the first decision tree, you will start with a root node, but you do not know that out of these four variables, which one to start with. So as I already mentioned that based on the information gain, for whichever variable the information gain is high, you will choose that particular variable into the node. So now let's see, they have calculated, जैसे हम लोगों ने अभी information gain calculate किया, by the same way they have calculated the information gain for outlook, temperature, humidity, and wind. And we can see that information gain for temperature, humidity, and wind is quite low, whereas information gain for Outlook is high. So that means I will start with Outlook. So by the same way, now I got the root node. Now I have to branch it based on the criteria that is there in Outlook. So there could be sunny, then overcast, and then you have rain. Now see, if you choose to be sunny, if you choose that your Outlook to be sunny, what are the classification results that you can see? You can see two are you do not play tennis. Then you have another representation which basically tells you that do not play tennis. But in this particular case, in D9, you can see that the attribute says even though it is sunny, play tennis. Again, in case of D11, you can see that even though it is sunny, you play tennis. So that means you can see in the next node, if you choose these to be the next node, you can see just by choosing sunny, there are some sort of ambiguity. There are 50-50 chance. So you just cannot use sunny to be the main classification to be incorporated in the main classification rule. So then what you have to do for sunny, after you have chosen the sunny, you have left with you have left with three other entities, that is temperature, humidity, and wind. So in these nodes, there will be either temperature or wind or humidity. Now, how to choose them? Again, what you have to do? Again, you have to. So over here, what I have already just said, that if you choose to be Outlook as sunny, you can see there are uh, two results which basically tells you to play tennis, and three results which basically tells you you should not play tennis. So this 2 plus basically means the yes class, and 3 minus basically means the no class. So that means over here, just by choosing sunny, you will not be able to classify the data, क्योंकि यहाँ पे ambiguity है, because finitely you are not able to classify using sunny. Let's see overcast. अब overcast के लिए, if you see D3, it is saying yes. Then D7 overcast में, again it is saying yes. Then overcast is D11 and D12 and D13. So all are saying yes only. So that means with overcast, you are able to classify all of them correctly. So this is non-ambiguous. So over here, you can stop the tree. So over here, this particular branch, this branch will be stopped because you are able to classify all of the data that belongs to overcast correctly. There is no ambiguity. However, in this particular case, if you see that if you choose your data to be sunny, then you can see out of 5 data, 2 of them are saying yes, 3 of them are saying no. Same as for the rain case. So that means in these two branches, in this one and in this one, you again have to further expand the tree. That means you started like this. Here it is stopped. This is stopped. But here you have to grow. So to grow, you again have to create 2 nodes. And then the next question is what you should put in these particular nodes. So for that, now your Outlook variable is gone because you have put Outlook over here. Now you have to see out of these 3, what should be put over here and what we can put over here. So if you go to the next slide, you will see again, they are now considering temperature. Inside temperature, there is high and low. Again, you have to calculate all these gains for humidity. In this particular slide, in the previous slide, they have calculated gain for temperature. So based on this, you have to expand the tree, and you can see that out of temperature, humidity, and wind, the highest value is basically given by humidity. So in the next phase, in the node, you have to consider humidity as the next node. So you can see you had sunny, then you have calculated all the information gains, and from the information gain, you can see that information gain for humidity is high. So that means you have to place humidity in the node. So by and large, the information gain basically tells you that which of the input attributes to consider for classification. So you have to start with root node. In the root node, you have 4 particular possibilities: outlook, temperature, humidity, and wind. And which one to choose, that will basically tell you this information gain. For whichever variable information gain is higher, you have to keep that particular variable in the nodes. And subsequently, you can increase the width of the, increase the depth of the tree. So this is what basically information gain signifies.
Thank you, sir. Thank you, sir.
Okay. So what we are discussing is basically how is pruning used to prevent overfitting in the decision trees. So in majority of the machine learning and deep learning models that you will basically see in the upcoming lectures as well, you will see there is a problem called overfitting, and already we have discussed what is overfitting in the previous lectures as well, that while training loss, but while predicting with the unseen data or the validation data or so as to the test data, you will see your model is not able to perform well, and it is basically yielding a significant amount of loss. So that means on the training set, it is performing very well. However, in the unseen data or validation data, it is not performing well. So the loss is higher over there. Now, to prevent this particular this sort of overfitting condition, in the previous weeks, for example, in logistic regression, we had seen that we can use different sort of in case of linear regression, we had seen that to reduce the overfitting, we can use different sort of regularization techniques like L1 regularization, L2 regularization, etc. Now, in case of decision tree, how we can prevent the overfitting. So as you have seen, let's say, while training the decision tree with a particular data set, you have, let's say, your decision tree somewhat looks like this. So let's say this is what your decision tree looks like, where this is the root node, and these are the leaf nodes, where we do the classification. Now, after you train the decision tree, now this is basically after training of decision tree, you have got this structure. Now you have to find that which of this particular connection is redundant. And what do I mean by redundant? That is basically, let's say, uh, you have a situation like this. So you are doing classification for A. Here also, let's say you have two classes only, and there are three attributes. And this particular node also, this basically, let's say, does some classification for class A, and the third one do the classification for class B. And let's say your classes are, you have two classes, binary classification problem, class A and class B. And you have an input attribute, let's say three input attributes, let's say xi. That could be x1, x2, and x3. Now, based on x1, x2, x3, you have to predict whether the data belongs to class A or class B. Now, based on this sort of data representation, let's say your decision tree looks like this. Now, over here, you can see that this particular node and this particular node, both of them basically do the classification in favor of class A. And this one solely do the classification for class B. Now, as you can see that out of these two, you can choose any one of them. Out of these two cases, you can choose any one of them, as because both of them are doing classification for class A, classification in favor of class A. So that means one of them must be redundant, which is not that much required. Anyway, using both these nodes, you are doing classification in favor of class A. So it will not matter if you choose a redundant node. So in case of pruning, this is what we do. After we train, we get a structure like this. Then we try to see that which one is, let's say, we try to see which one is redundant. That means which can be removed, and even after we remove, that will not, by and large, it will create an effect in the classification accuracy. So in this particular case, if you can see that, let's say this is redundant case, and if you even if you choose this particular node to be redundant, or this particular connection to be redundant, and what it will do, remove structure from the decision tree, even though what it will effectively, there will be no change in the classification process, because you can see that this particular side, it will do classification in favor of class A. So this one is, let's say, redundant. So what you will do, what pruning will do, it will remove this particular classification node from the decision tree, so that your decision tree will be less complex. And in the overfitting lecture, we had seen, let's say this is complexity of model, and this is, let's say, loss. And if this is the training loss, and if this is the testing loss, you can see when the model is complex enough, then you see the overfitting issue. And you can consider that initially, when you had this particular branch, then you had three branches. Now, using pruning, what you have done, you have removed this particular branch. So that means in some way you have reduced the complexity. You have reduced complexity. You have also reduced redundant information from the tree itself. So this is how you basically do the uh, what you call pruning to reduce the overfitting. So let us see how what are the options they have given. By limiting the depth of the tree, but the limiting depth of the trees will not basically, it is not associated with pruning. By removing the branches with low information load. So that is what we have talked about. So we have to find that what is the redundant branch. So this is the redundant branch. Let's say it has information gain quite low rather than these two branches. So over there, what you will do, you have to remove this particular branch. And while removing the branch, you will reduce the complexity, reduce the redundant information, and hence you can prevent the overfitting. So therefore, this is the correct answer. Okay. So the next question states that where does the additional variable are added in hidden Markov model? So uh, again in the week's lecture, if you have seen the hidden Markov models class, you have seen that Professor MKB has given example for speech signal analysis or temporal data analysis. So over there, the let's say the hidden Markov model had a structure like this. So this you can see that this has some sort of a temporal data notion. That means the current data is basically dependent on the previous data. So that is how we deal the temporal data. For example, uh, you have seen, let's say, stock market data prediction. So what they do, they basically try to see uh, some sort of previous trend in the data, and based on the previous trend on the data, they try to predict the new data. So that is what we are doing. Let's say this particular data we want to predict, we can predict using the previous data, this one, as well as the previous data, this one. So that means if you have to create the new data, you have to see the previous data. So that means based on previous data, you can create the new data. So this basically, so that means xt is dependent on, is let's say dependent on the previous data xt minus k. So that means this has a temporal relationship. So if you choose to predict a new data or an additional data, so that you can connect in the temporal as a temporal model. So therefore, again, this particular data will basically dependent on this particular data, this one, and this one. So therefore, if you want to add some sort of new additional variables, that you can add in the form of temporal data. And in general, hidden Markov models are quite used in the in any biological data processing as well, biomedical signal processing as well.
So whether we have to calculate the probability of each individual, each event separately, and then we have to multiply, sir.
Yeah, we have to calculate the sort of like these state transition probabilities, and the state transition probabilities you can start from this side, and then you can start basically uh, writing the probability of sequence based on the probability of sequence formula, and the values have been given over here, and then you have to just multiply them. So if I just start writing them, so it would be, we can start from this particular direction, right to left, and then we can write S3 given S2, probability of S2 given S1, probability of S1 given S1, probability of uh, S1 given S1, probability of S1 given S3. 1 second. S1 given S3, probability of S3 given S3, probability of S3 given S3, and then you have probability of S3. So this particular equation, you can see the week's lecture as well. So Professor PKV had given an example like rainy and dry. So based on that rainy, dry, he had taken some example like this. By the same way, I just have rewritten the equation over here. So we have all these values. We can derive all these values from this particular matrix. So one such example could be, let me just show you P S3 given S3. So S3 is basically this particular value, that is 0.8. So you can just put 0.8 over there. Similarly, let me just show you PS1 given S1. So already I have written A11 means PS1 given S1. So you can put 0.4 over there. So after you just put all the values, so let me just put the values 0.1, 0.2, 0.1, 0.4, 0.3, 0.8, 0.8. And now the value that is, so this all conditional values will get from the state transition matrix. Now, what about the last probability of S3? So that is the occurrence of the S3 condition, occurrence of the occurrence of S3. So S3 occurs at, we are now at the D1 condition because we have started writing from this particular side, and we have ended with P of S3, which is at D1. So you can see in the question they have written, given that weather on day 1 is sunny. So that means they are finitely saying that at day 1, the probability, the day is sunny itself. So the probability is maximum. And what is the maximum value of probability? In the notion of probability, probability ranges from 0 to 1. And as because they are finitely saying, so that means this 100% that the day itself. So you should know that how to extract these nomenclatures, PS1 given S1, PS2 given S2, all these things. And then you should also have to know that how to write the probability of sequence. Now, after you get the probability of sequence, you just multiply all of them, and then you can get the final answer. That's it. Okay. So with this, we have solved the, sorry, we have solved the this week's quiz, week 5 quiz. And as I told that I will be showing the demonstration of SVM using some sort of, what do you call, the synthetic data set as well as the traditional in general data set that we have seen in the previous classes as well, that is MNIST data set and Cypherton data set. So in SVM's week, we have seen, if I just show you the problem, we used to give you the examples like this, where the data is quite linearly separable. And we could have put a straight line over there or the decision boundary, and the decision boundary will basically classify these two classes pretty well. And the main target was basically to find the optimal find optimal decision boundary. And based on the optimal decision boundary, based on SVM, you will basically try to find the optimal decision boundary. Now, tell me, for a XOR gate, can you classify them using a linear decision boundary? For a XOR gate, let's say you have two input attributes, x1 and x2, x1 and x2, and you have the class identity as y, so 0, 0, 0, 1, 1, 0, 1, 1. So the outputs are 0, 0, 1, 1. So if I just plot them, you can see that 0, 0 is over here. Then 1, 1 is over here. That is, these are the 0 class. Then you have 0, 1. So which is the class 1, and 1, 0, which is the class 1. So now tell me, is this particular problem, it is a linearly separable problem or it is a non-linearly separable problem?
Non-linearly separable.
Yes, so this is a non-linearly separable problem because you cannot put a straight line in between. Let's say if you have to put straight line, you have to put two straight lines, but which is not optimal because to classify them, you have to put two parallel lines because there is no unified decision boundary. But in general, in case of uh, SVM, we try to find a unified decision boundary, which is an optimal decision boundary that gives the highest margin for classification. So you can see these sort of examples as well, XOR gates and XOR gate based examples as well, through which we can see that how SVM basically performs. So you have also seen that this particular SVM basically a linear SVM. And you have also seen another class of SVM that is nonlinear SVM, which is also called polynomial SVM. So there you have seen cubic SVM, quadratic SVM, if you recall from the lectures. So you have seen polynomial SVM over there. The subclasses are cubic SVM, quadratic SVM, etc. So we'll use this cubic SVM, quadratic SVM, as well as this linear SVM to see the classification results. Fine. Now, for this, you generally don't have to write code by yourself for SVM. Let's say you want to implement SVM. You might think that I have to write the full code from scratch. So that you do not have to do because already in Python, there is a package called scikit-learn. Within scikit-learn, they have already incorporated the functions for SVM. What you have to do, you just have to call that particular function, and then you can declare that whether you want to do with linear SVM, polynomial SVM, etc. And then you have to do the classification. Majorly, SVM, KNN, etc. All these things are effectively would be a 3 lines of code in general. So let me start with this example. So I will walk you through what I have done over here. So in general, we have to first import some libraries for basic data handling. So import matplotlib.pyplot. So this will help you to plot the data, to visualize the data. And then I have imported NumPy. So NumPy is basically to handle any sort of basic array operations or matrix operations. Then I am creating a custom data set. So this is a 2D two-dimensional plane, that two-dimensional data set I'm considering. So that means I will be creating some sort of data like this, which has two axes, and based on two axes, I have some data points. Okay. And each of the data point, for example, this particular data point belongs to class 0. This particular data point belongs to class 0. In this way, I have some classes called class 0 and I have several classes for class 1. So this is a binary classification problem. And then what I am doing, I'm plotting those data samples. And let us see how it basically looks like. Yeah. So this is what the data set looks like. So the darker points belongs to class 0 and the yellow points belongs to class 1. Now in just by the basic visualization itself, you can see that this is very hard to classify so far as linear decision boundary is concerned, because this is somewhat a non-linearly separable problem, but still we'll start with linear SVM and then we can see that can we do better classification with the non-linear SVMs as well. So we'll start with from sklearn. So as because I told that there is a library called scikit-learn. So this is also called sklearn. The shorter version of the library is called sklearn. From sklearn, import SVM. So this is the powerful line. Whenever you just call this particular line import SVM, so that means the whole code or the whole formulation for SVM that you have seen, like the Lagrangian formulation, all the mathematical operation that was there, they have already coded over here. This particular function is basically represents the whole operation that you have seen in the theory class. So in general, you do not have to write anything by yourself. And as well as I want to show you the decision boundary surface. So that is why I have also taken another function or method from the sklearn. So that is from sklearn dot inspection, as because I will be inspecting the decision boundary. And then import decision boundary. I think my internet is somewhat fluctuating. Okay. Then I have created a custom function. And let me just walk you through that what I have done. So this is a function. So to write function, we have to write definition. So def basically the instantiation of a function. So the definition of the function, the name of the function is plot training data with decision boundary. And the arguments are kernel. And I will tell you that what basically kernel means, the axis, the title of the figure, and the support vectors. So we have to train the support vector machine. So to do that, so I have also commented that train the SVC. So inside SVM, the further method is called SVC. So the support vector class. So by which you can actually do the classification. So it has two arguments. One is kernel. So here you can put either linear kernel or cubic or quadratic or any sort of other polynomial. And there is another term called gamma. So this gamma will later on talk about what this basically gamma means. And then you have declared the sort of SVM. And after you declare the SVM, this dot fit basically means the training of the SVM model. And what you want to train it with? Input data and output labels. After that, what you will be doing? You will be plotting the data, plotting this particular figure, this particular one. And as well as you also want to see what is the decision boundary. So that is why I have written that decision boundary from the estimator, because you have an estimator that is the SVM based estimator, and this is a pretty standard convention. You can go to the sklearn's library, and then you can see all the arguments that basically means what basically it means. Now, at the same time, from the decision surface, what basically SVM will give you, we will also try to see that what are the support vectors it basically tries to look at, because SVM is all about finding the support vectors as well. If you because margin will be maximized based on the support vectors. So that is why we also try to intend to see what are the support vectors. So this particular method basically deals deals with the support finding of the support vectors. And then you plot all the data and you have some sort of legend like what are the classes, either class 1 or class 0, and the title as well. So the title is decision boundary of kernel. So this kernel would be either linear or it could be any sort of radial basis function, polynomial kernels like cubic, quadratic, etc. I don't think so radial basis function have been taught in the class till now, but let us consider we'll just use some functionalities and we'll try to see that what out of all the kernels basically give you the best result. So let us run this particular function. Now, based on the function, now let us try to see the result. So what we'll do, we'll call the function and the kernel, we just have to declare the kernel. So let us now start with linear kernel. So when we use linear kernel, you can see that your data was looking like this, right? And your decision boundary is this one, this middle darker one, and you have two classes over here. This is for class 1, this is for class 0. And you can see that these are the support vectors that are lying on the edges of the these are the support vectors, and you can also see that there is a misclassification. As because I was telling that the problem at hand is strictly it is not a linearly separable problem, because if you intend to draw a line over here, obviously you will do a misclassification because this particular sample will be misclassified. This is what is basically happening over here. You can see that this particular sample is misclassified. So this is a drawback for linear SVM. That linear SVM will only perform very well. It will do very well, do good classification only when your data is strictly linearly separate. Otherwise, you will see some sort of misclassification. Likewise, you have seen over here. This particular sample is misclassified. Now let us see what is uh, using polynomial kernel. So when we use polynomial kernel, so over here you can see the equation. So you have two input features, that is x1 and x2, and you are multiplying them. So this is basically an x squared term like this. And I have also written that this is the degree of the polynomial. So over here, this is d. And when you write poly, the d is equal to 2. So that means this is a quadratic case. If you choose the degree to be 3, so then it would be a cubic polynomial as well. So over here we have written that here we use default value of degree, that is kernel, with degree equal to 3. So if you run this, now you can see initially when you started with linear kernel, so over here you can see the linear kernel was not able to classify this particular sample. It is due to the inherent property of line, because you cannot bend the line over here. Because the function of the mathematical representation of line is y equal to mx plus c. So you cannot bend this particular line like this. You cannot do a zigzag line over here because you want to extract a unified decision boundary. However, when you use polynomial kernel, so over here, for example, you have done a polynomial kernel based representation. You can see your decision boundary is more complex. So this is somewhat a wiggly line over here. And these are the support vectors. And you can see that using this particular decision boundary, you are immensely increasing the margin of the classification. So over here you can see that the margin of the classification for both the classes have drastically increased. So that means if your data is non-linearly separable, it is always preferable to use polynomial kernels, because linear kernels will not be able to serve the purpose in major of the cases. Now let's say there is another case, that is radial basis function. So over here, the radial basis function is even more complex. It gives you distinct clusters. So that means you can see major portion is basically allocated for class 0, whereas specific segments are grouped as class 1. So this is what basically radial basis function means. However, we have not discussed radial basis function in the class. And uh, why this sort of representation is, so you can see some sort of a circular representation, not strictly circle, but some sort of a circular grouping. And this is basically what happens in case of radial basis function. So we use some sort of a L2 norm over there, that is x1 minus x2's L2 norm. So this basically gives you some sort of a notion of circular clusters. So that is what we can see over here. Now this is a custom dataset that we had created. At the same time, in the theory part, we just have taken a four data-based XOR gate classification. So over there, we had seen that this problem is strictly non-linearly separable problem. And that is what we will simulate over here as well. So this is for a XOR dataset. And as because machine learning, deep learning experiments are done on huge number of data points. So we have considered 300 such data points. So that is x np.random 300 by 2. So that means we'll be constructing 300 such data points with 2 dimensions. And the logical operation that we are using is XOR to create a XOR data set. And then what we are doing, we are that is plot training data with decision boundary with linear kernel, polynomial kernel, radius basis function kernel, and sigmoid kernel. And we'll see that whether these particular SVM functions can able to classify this XOR data set well or not. So let us just try to see the visualization. Okay. So over here you can see that the problem is quite challenging. This is the data set, and the data set is majorly overlapping in major cases. So just drawing a simple line will not help you in classification. So you can see that you are doing severe amount of misclassification. If this side is for class omega class 0, you can see majority of the points, a huge amount of point belongs to class 1, which are misclassified. So that means linear kernel are not able to do well in this particular case. So as polynomial kernel as well, because in case of machine learning, major of the cases, you will see you are learning the weights, which is a stochastic process. You use basically the gradient descent based method to learn the weights. In polynomial case also, you are not able to classify majority of the, even from the previous case, you can see the linear classifier still somewhat does a good job than the polynomial case. Because over here, you are trying to fit higher degree of polynomial. And as because you are trying to fit higher degree of polynomial, you are not able to understand anything, because you are creating a very complex model which is not able to understand anything. In the third case, you can see that using a radial basis function, you are strictly creating some specific clusters or some specific decision surfaces, which basically does the best classification among all. Even sigmoid also, you can see you are doing several misclassifications, but in radial basis function, it is the optimal one. So in general, you will see in majority of the cases, as because we have not dealt with radial basis function yet, but you will see in general, people use radial basis function pretty widely for this sort of classification purposes. Okay. So this was on what you call the uh, for a synthetic data set. Now let us now move to standard data set, which is IDs data set. So the IDs data set is a predefined built-on data set that is there in the sklearn itself, scikit-learn package itself. So again, I'm importing the matplotlib sklearn for datasets and SVM because I will be using a predefined dataset which is there in sklearn, and that is ID's dataset. So that is why I'm calling from sklearn import datasets. This particular method we also have seen in case of KDAS as well while importing the MNIST dataset and Cyber10 dataset. After that, again, I'm calling the decision boundary method from sklearn.inspection. So next, I have to load the dataset. We also already know that how to load the dataset. In probably lecture 2, I had shown you that you have to call dataset.load underscore the dataset name. So this is what we have done in MNIST as well. We used dataset.load MNIST, and similarly we are doing dataset.load IDs. Then IDs dataset has 3 features. Now, if I use 3 features, it would be a bit difficult to show these classification boundaries, because then the dimension would be 3-dimensional. The pictures will be in 3 dimension. So that is why I am just considering 2 features. So that is why I am writing take the first 2 features. We could avoid this by using 2-dimensional dataset. So in the previous case, we have considered 2-dimensional dataset. However, ID's dataset is a 3-dimensional dataset. I am just only considering first two features, such that the problem still remains in 2 dimension. As well as I need to collect the labels as well. So this is what I can get from this particular variable y equals to IDs.target. And then I can write the model, that is kernel, linear kernel, linear SVC with maximum iteration. I can do the optimization function go till 100 iteration, then RBF and polynomial. And then these are the titles for the linear kernel, the linear kernel with iteration 100, radial basis function, and polynomial with degree 3. And then we will show that how the decision surface looks like. Pretty similar to this one. We have taken 4 cases and we'll try to see that how the decision surface looks like. So over here, you can see we have 3 classes, and the 3 classes, if I use MNIST dataset, already we have seen in the theory classes, let's say you have 3 classes. To classify them, how many decision surfaces you need? You need 3 decision surfaces, 3 decision boundaries, so to say. So over here as well, you can see we are trying to draw 3 decision surfaces. And here you can see that this particular class is classified pretty well. Red class is not able, we are not able to classify these 2 classes. We are doing major misclassification in linear kernel. Similarly, when we increase the number of iteration for the same classifier, we can see that somewhat we are able to increase this particular area. So over here you can see this area, this red area is increased in the second class. So that means with iteration you are trying to learn more information. Then for the radial basis function, you can see that it is creating some sort of a peculiar shaped decision boundaries, as because these functions will not give you linear boundaries. These will give you some sort of a non-linear boundary. And so as the polynomial case as well. So they are trying to fit with some parabolas. And again, you are not able to classify well in case of degree 3 polynomial as well. So out of all these, majorly, if you see the confusion matrix, the radial basis function basically outperforms all the other methods. Okay. Now let me show you another some somewhat a difficult problem. So you can understand when you have two class problem, radial basis function does very good. It is able to classify with almost 100% accuracy. When you increase the number of classes, you can see the performance starts degrading. Why? Because machine learning models basically rely on handcrafted features. You extract some features and based on those features, you try to classify. On the first lecture, we talked about good features. Good feature means which do not overlap with each other. So over here, you can see the blue one are quite separated. These features are quite separated from the other two cases. But these red and white classes, their features are quite jumbled up, or they have quite similar attributes. So there is a overlap in between red class and white class. So that means, this uh, uh, these features are not good for classification. And if you use these particular features for machine learning classifier, obviously it will not be able to give you a good classification result. That is why we need deep learning. And that we can expect in probably week 8 or 9. So from week 8 or 9, we'll see deep learning based lectures. Now in MNIST dataset, already I have shown you that how to import the data set and etc. So I'm not discussing these things. And the main target is basically from the MNIST data set, I'm doing, I'm using the linear SVM. And I will try to see in MNIST data set, they have the digits of 0 to 9. That means a total of 10 classes. And we are extracting two features. And based just try to see how the result looks like. So this you can see that test accuracy is 53%. And this is the confusion matrix for the 10 class classification. And you can see that in majority of the cases, you are doing huge misclassification. That means, for example, for class 8, you are only able to classify 7 samples correctly. Majority of the class 8 images, you have predicted as class 1. So that means you are doing misclassification. Here also for class 5, you have only able to classify only 4 samples correctly. Majority of the classes you have either classified as class 1 or class 8. So that means you are doing major misclassification, and the test accuracy also tells the same, only 53% accuracy. This also shows that these sort of machine learning classifiers are not very well for doing classification or for doing basic classification for a wider group of class entities. Let's say over here you have 10 classes and you are extracting 2 features to classify them. And if you see the features, now you can see there are total 10 classes and all of the classes are jumbled up. You are not able to classify them well. And the decision surfaces also, they are quite overlapping with each other. And that is why majority of the classes are not able to classify it well. So these are some drawbacks of the SVM SVMs that we have shown. So even if you use some other kernels, let's say radial basis function or let's say polynomial kernels, there also you will see that you will not get much of an improvement, because with the number of classes, you increase the complexity of the problem. You increase the there is a chance of feature overlap. So you just cannot use simple features fed to a SVM to classify them, and they will not be able to do good classification. So for that, you need some advanced techniques, which we currently use in nowadays, that is deep learning based techniques. Okay. So I will be uploading this particular notebook in my GitHub profile as well. So from there, you can download the uh, Python code and then you can run it at your side as well. Okay. So with this, I think now we can end the session. If you have any queries, you can ask. Otherwise, we can end the session here.
Sir, I have one doubt in 10th problem, sir. Assignment problem.
Yes.
Sir, here you have written the probability of output model S3, 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 comma like that. After
Yeah.
that, how you are writing this conditional probability, sir? Probability
Yes.
of
Yes.
S3 given S2, that how you have written, sir, that I cannot
Yeah.
understand.
Yeah. See, the main thing is, let's say you have this process. Let's say this is S1, S2, S3. S3, S1, S2, S1. So this is called probability of sequence. Oh, sorry, it should be from S1, S2, S3. Let me just rewrite this S1, S2, S3. So how we write this particular thing in this way? So you can see S3 is coming from S2, right? So that means S3 is dependent on S2. Then similarly, S2 is dependent on S1, right? So I can write P S3 given S2, P S2 given S1. Then when you reach at the, so we start from the right hand side and then we go to the left hand side. And when we reach the last one, so we consider that the sequence has been started with this particular thing. That is what we can see over here as well. The sequence, this S1, S2, S3, this particular state have been started from S1. So we'll consider the occurrence of S1, because as S1 has occurred, it generated S2, then it generated S3. So therefore, we'll start writing the conditional probabilities like this as S3 dependent on S2, S2 dependent on S1, and we have now reached the farthest point in the right hand side. And now we can consider that based on as S1 has uh, took place, then only this S2 and S3 basically generated. So we will be considering the probability of occurrence of S1. So this is the formula. This is how we write the this particular probability of sequence. So if I go to the previous slide, so I have started from this side. So S2 given S3 given S2, S2 given S1, S1 given S1, S1 given S1, S1 given S3, S3 given S3, S3 given S3. Now I have reached at the farthest point in the right hand side. So I will consider that from S3, all the states have been generated. So now I will consider that P of S3.
Yes, sir. Thank you, sir.
Okay, and for the again, let me just tell you, in the last week, week 4, some of the answers were incorrectly marked as correct by NPTEL team. So I have conveyed them. So they have confirmed that some of the questions are wrongly marked. So they are re-evaluating all of the questions again, and they will update the website, and your marks will also be updated by end of next week. So you will get marks for the incorrect questions.
Okay, thank you, sir.
Okay, so let me turn off the recording.